is exceptionally good.
I moved it over so
And Matt,
Okay, thank you.
we'll go ahead. I know some of you are still finishing up collecting data. I'll put, I entered some up there too, so we'll get that for sure before. You don't actually need those numbers until you go to the computer lab. And so it's just easier to collect them in here before everybody gets all crazy on the computers. A couple of things, and I know it was a long email. There was a lot of data in there. I just wanted to see if you want to look at the data, but you just want to filter through whatever suggestions there are. On the homework, the biggest error was not in calculations. There's a couple of the calculations were off. I think there was one that should have been 0.86, and in like 2 or 3 we had 0.84. And so either that means you entered it in the table wrong, or you somehow put the formula in and overwrote something that was there, or there was an extra number left over. But for the most part, the homework was all correct. The thing that people and I put notes on there, but when the question says, is the data statistically significant? And that is the same as accepting the research hypothesis. So when it asks that question, is it statistically significant? That means you rejected the null. The null means they're not significant. There's no relationship. So if you reject the null, then it's statistically significant. And so that was, most of you had it all correct. Like, and you would say accept the reason, or you'd say reject the null, and then you would say it's not statistically significant. So like you're saying opposite things. So just be careful with the words there. I added that. I'll probably add that to the chart then for the next time around that I teach that. But if you want to add that to your chart there, I think for t-test, that's on the left column of the t-test. And so I think that would be helpful to have in there. And on the test, if you have specific questions about problems, I can talk to you during the break or when we're working in the computer lab. But for the most part, the scores are really pretty consistent. If you miss something, oftentimes it was carried. Like, so for confidence intervals, it's easy to use the wrong mean. When you're doing a confidence interval, you want to do the sample mean, not the population mean, because you're adjusting. Whereas with a z-score, you use the population mean. So that can get a little confusing. I would suggest going to that formula sheet that has the words on it and making sure you get the right words and not try to look at the symbols. You can, but there's a better chance that you'll get that correct if you use the words, I think. So, so there's not a test over these things. It will be on the final. So that's the only time you're going to be tested. My suggestion in that email, because some people have been asking about getting ready for the final because it's cumulative, my suggestion would be to print off the topics on the final and use that as like a guide sheet. So if you see a question and you know how to find it, or you can get it, if all you need is the formula and you know the formula's on your formula sheet, I wouldn't write anything down. You like formula sheet, boom. If there's ones where you want to reference page numbers, you'll have all of your stuff. So you'll have, your book, you have your tests, your homework, whatever but that can be too much. You don't have a way to filter through it. And you may work with somebody, no more than a group of 3. You may work together on the final, but if you're going to do that, you're going to need to work together on the whole thing, not do the whole final and then compare answers, because in that, the person who knows what they're doing basically just gives the answers to the other person. I'm okay if you know what you're doing and the person you're helping doesn't, and you explain it to them. That helps both of you. So if you want to work together on the final, you can. It's not always as easy as it seems, because you do have to be able to work with the other person. You might get frustrated, but you are welcome to do that. I'll let you choose that. You don't have to tell me ahead of time if that's what you're going to do. We will be in the computer lab for the final, so we'll come up here first, not unpack, just double check about some, like, lightly unpacked, right? semi-unpacking. Levels of, I need to put, you're zoning out on me? I was making a joke about it. I need to have levels of unpacking. Okay? So tonight, we'll do all of the, like, going through the PowerPoints in here, and then we'll go, so I'll show you some stuff on the computer in here, and then we'll go to the computer lab and actually try our hand at this. And tonight is, I know I say this every week, but this is some pretty good stuff tonight. You're going to learn the most overused word in English language, incorrectly used as correlation. So you're going to be able to not make that mistake and set people straight all at the same time.
Oh, so I would make residential.
I'm sure there'll be, oh yeah, that's definitely not right there. Okay, let me get this. So we will cover a whole bunch of stuff where generally if you were doing this you would take more time because you'd have to work out the calculations, but since we're not working out, we're letting the computer do the calculations, we won't. Okay. All right. Let me dim the light a little bit. I even brought my laser mouse, but there's no place to plug it in, so I just have to make this into a laser mouse. By the way, if you want to make your own posters like this, there's actually, if you go to Most Interesting Man in the World, you can type in your own quotes and make your own stuff. It does not, this is not what the final exam is going to look like. Champagne crunches. All right. So the whole thing with the word correlation is it only shows a numerical relationship. It does not show a cause. And a lot of the examples in here that are trying to warn you heavily, and this little joke maybe will be funnier after you learn more about correlation. Maybe it won't. And that says week 4, but that's on the whole thing. So we're gonna talk about what R is. R is a correlation coefficient, and we'll calculate that. We'll analyze it. Either someone gives you it and you tell them, kind of like Cohen's calculation. They tell you a number and you say whether it's small, medium, or large. Same kind of idea. So we'll anytime it says compute, you're going to be using Excel, and then there's a thing called coefficient of determination, which is a fancy name for squaring the correlation coefficient. And we'll also use the computer for that. And test hypothesis about population, we're going to do a fast hypothesis test. I think that we just cut that out of the homework so that you can get ready for the final if you want to. So a key with correlation, it has to be two discrete, or it has to be two numerical variables. It could be continuous when you decide. So you can't do correlation with favorite colors and number of people with favorite colors. It has to be something you can do a scatter plot with. So it has to be numbers to numbers. And when we do the second part of class, when we do the chi-squared, that can be a relationship, and it can be words to words. So numbers to numbers is correlation. A positive correlation is the sign of the R value, and usually we're going to talk about linear correlation. So the closer it looks to a line, the better the correlation. And the values of the correlation, the strength is from 0 to 1. So you can also go from 0 to -1 on the other direction. So a correlation of +1 and -1 are the exact same weight. They have the same value. One of them just going like this, one of them is going like that. We'll show you some pictures. It'll make a little more sense. So we have a scatter plot of family income and students' average grade. And so you can see, and they even, they didn't start at 0, so that's sometimes a caution, but if you want to be able to see your dots on one screen, sometimes you change the scale, it's okay. As long as the scale at least remains fairly consistent. Like I would see some cautions here, like this is 25, and that's 20, and that's 15. Like the scale is kind of funky, but we see the dots. Okay, they plotted the points. We're going to trust that they gave us those points. If you could take a ruler and try to go through the very middle of all that data, that's a correlation. It's a line of regression. It goes right through there. If you can see kind of a linear shape, then there is some correlation. Okay, so there's a numerical relationship. As family income goes up, so does the student average grade. So you can see that numerical relationship. That doesn't mean that income determines grades. Okay, that just means there's a numerical relationship. So we have several good examples of misunderstanding. So more and more young people are attending high school and colleges today than before. There's more juvenile delinquency and more alienation among the young. It's clear that these young people are being corrupted by their education. Because we have more people here, you can show a numerical relationship. Ice cream sales correlate with the number of people who drown. Therefore, ice cream sales cause people to drown. Well, generally, when ice cream sales go up, the number of people swimming also has gone up. So the likelihood of drowning probably goes up. So those are not. So correlation doesn't exactly mean there's a cause. So my favorite one. That's Sir Mix-a-Lot. If you don't. Misunderstood correlation. And so sometimes it's kind of interesting to try to figure out why it's a misunderstanding. So this one's trying to show this graph that as chocolate consumption goes up, that you have more Nobel laureates per the population. And it shows the R value is 0.79, which is pretty high. Well, when you start looking at, then it marks it with the different countries, then you see that your data may not be the best data. Well, Switzerland, way up here. Well, Switzerland they eat a lot of chocolate, and they've had the most Nobel laureates, not necessarily a cause. In China, so one variable could affect this data. Like if your country doesn't eat chocolate, you're out of the running. You know what I mean? Like even if you have drowning deaths, consumption of ice cream, that's always a good one. The one that I do with the teenagers is the length of skirts. As the length of skirts gets shorter, the sale of ice cream goes up. And so I say, what does that mean? And they're always like, because they have someone standing out there selling ice cream. Now think about what does it mean? And stop and talk about, no, it's not the person selling the ice cream. It's the fact that it's summer. Global average temperature versus number of pirates. Now this one is a bad scaling factor too. If you notice this one, look at the scale. It goes up and then it goes down. I'm not sure whether it's 35, 45, 20, 15. I don't know if that's a misprint. Totally meant to mislead someone that the temperature's rising, but we have less pirates. Eating chicken makes you go to the moon. Okay, so now the serious stuff. So you plot two scaled variables. It's the relationship between the two. The name correlation, correlation. Co means together, same together, relationship together. We will measure the strength of correlation using R. It's called Pearson's correlation coefficient. And then we'll draw a line and we'll have an equation of the line. The Excel thing that we set up will give you an equation too. So our whole goal is to talk about how strong the correlation is.
Yeah. Why are they using the word regression?
Because regression is what you use to find the line.
I mean, return to the line?
No, kind of. It means, you take the value and you subtract the means. So since there's an x and a y value, it's a process of subtracting and squaring the means. Kind of like finding standard. It's kind of like finding standard deviation. But basically, the computer will give you the best fit equation. It gives you the best fit line. It's called a regression line. Regression is the process. So positive correlation, if you remember much about graphing lines in algebra, this is a positive slope if we're increasing from left to right. So this would be a positive correlation. You can kind of see, you know, the dots, if you set your ruler right down the middle, you have about the same number on each side. It might go through and depending on, it might not hit any of your points, your best fit line. And this is a negative correlation. This is the one people mess up sometimes because they think about a negative, like a negative effect or cause or something. Negative correlation just means as one thing gets smaller, so does the other. Coffee sold, temperature raise. Beer sold, or temperature, as the temperature goes up, the amount of coffee sales goes down. So that's a negative, it's a negative slope. Which makes sense. The amount of beer sold is increasing as the temperature goes up. Low scores relating to low scores does not mean negative correlation. That's the one where it can get a little tricky. Because if you have, like if you think of a picture, if we just any two, we don't even have to know what these variables are. But if you get a low score related to, as this goes up, low score, that's actually positive correlation. So negative correlation would be as one of the scores gets bigger, the other one gets smaller, or you can flip it. And for you, you're going to look at it and see. It's going like this, it's positive. It's going like that, it's negative. And our score will show up on the Excel document. You may have seen this when you were messing with the annoying histogram bar graph option Katie loves. It will ask if you want to add a trend line to the graph sometimes. A trend line is not correlation. If you notice, these are quarters, these are not. And so just because you have a bar graph with a trend line does not mean you have correlation. Correlation is numerical, some kind of scaled to scale. It could be, but generally it's coordinates that you're plotting. So specific points in time. Supposed to be positive or negative correlation? Positive, pretty strong, because if you see how many of these are really, the closer they are to the line, the stronger the correlation. So this would be perfect correlation because we could take anywhere on this line and put in one value and we'd get the other one. So this would be a correlation of -1 because it's negative correlation. Perfect correlation is -1. Perfect positive correlation is +1. So that would have an R value of -1. This would have an R value that is, I know a couple things, but I know it's positive, and I know it's decent correlation. Like if I put a line right here, they're fairly close together, so I don't know what it would be, 0.6, I don't know. Let Excel tell us if we have these data values, but I know it's positive and it's moderately strong because you can see that they're increasing together. These two are harder to tell. Because of the way they circle this, I think this is a negative correlation, but it's pretty weak. Like the line goes there, but the dots are not close to the line. And this is just probably no correlation at all. It's just a scatter plot, random. So here's the part that it's important for you to know in this. You don't need to be able to do this equation, so I wouldn't even write it down. We put this on here to show you where R comes from. It doesn't come from the little mice in your computer in Excel. It's a calculation. It's kind of like standard deviation. in how it calculates it. It does a calculation over and over and over again, only it does the products of the values instead of subtracting and squaring. But you need to know that the smallest correlation can be is -1, and the biggest it can be is 1. So same with when we were doing our t-test. If you got a t-test bigger than 1, something's wrong, unless you were changing it to percent. So 1 represents 100% in that. You don't want to know this formula. This is what you recognize it. The x value minus the averages of the x's, the y value minus the average of the y's, all for all the value. That's what Excel does. That's why we don't do it by hand. Okay? I'm going to skip right through that. Boom. Don't even look at it. Okay. When we have a longer period of time, we do this in the math class that I teach at high school, we have a few weeks, and so we'll do a small example where you actually calculate it. It helps you see it a little bit, but it's not good to try to cram that into one evening, and then you'd be disappointed. So again, talking about the closer R is to 1, stronger. Closer R is to -1, stronger negative correlation. These two have the same correlation. 0.56, negative 0.56, same correlation. One's positive, one's negative. The strength is the same. So this is just kind of a nice little chart to help you kind of a continuum of where things would fall. So for this one, 0.07, if you write in here, I mean really small, I would say very weak positive. You might not be able to even tell that there was a positive correlation unless your calculator gave you the number. Whereas this one, negative 0.89, is all the way over here on your continuum, so it's strong negative. Strong, very strong positive. Pretty weak. 0.12 is pretty weak. So that little chart's helpful. We'll talk about R squared in a second, and then there's actually a table that you can use. So in the words here, so the words can get a little confusing when you don't have a picture. Scatter plot shows a set of data points that fit very loosely around a line that slopes down to the right. So they're loose, slopes down to the right. So if you go back to that little scale, again, the closer you get to -1, the stronger the correlation. So if it's a loose correlation or weak correlation, down to the right, going to get -0.35 because it's going down to the right. Again, it's helpful to actually have the data points, not the words. But you see it in the question. You want to be thinking, which way is it? Is it getting bigger or smaller from left to right? Where do I go with it? This goes back to the silly examples, right? We can show a numerical relationship, but we don't necessarily demonstrate that there is a cause. It means you go back, and just like a lot of our other things, that means the data is significant and we need to investigate further. And this is the ice cream drowning desk thing. Okay, you say, yeah, I show there's a correlation here. The worst example that I can think of, and we talked about it maybe a little bit in class, was the Indiana state government they read a study that I told you about, the Algebra 2 students. They found a study that they surveyed Algebra 2, or they surveyed college students and found that nearly all of them had taken Algebra 2. And so based on that conclusion, they required Algebra 2, and they've been requiring Algebra 2, and it basically has made high schools try to figure out how we can get everybody to Algebra 2, because that's what you need for the Core 40 diploma, when the reality was there's more variables involved in that fact. The fact that they took Algebra 2 was not making them go to college, but they used the reverse You've heard people say correlation does not mean causation. Well, our whole diploma system in Indiana is based on bad correlation. No matter how much we try to explain to them that that's not the case. Okay, so we're going to do an example here. We'll look at so if you have we'll look at our feet examples here in a second, but the range can really affect it. So you want to make sure that your data is kind of clumped together, but not like a fist. You don't want to have all the way stretched out. There's something called interpolation and extrapolation, and I'll show you with the picture. It's easier to see. In your Latin, inter means between. So if you look at all your data, and anything between the smallest or the furthest left value and the furthest right value, if you're looking on your x-axis, that is called interpolation. That's between the poles. That is okay. You can more accurately do interpolation. If you go beyond that, you're extrapolating, and extrapolating is less accurate. So, like right here, if you have a 500 square foot house, using this trend line, it would say it costs $130. I don't know if that's or house per price. So it costs $130,000. And if you come down here and you say, well, I have a 200 square, it costs $120,000. Well, I don't have any data here. I'm using my line, trusting that my line stretches outside of the way. So extrapolation is always dangerous. When people say extrapolation and they're talking about data, I would avoid using that word. I wouldn't say I extrapolated from the data, because if you extrapolate from the data, you're making conclusions beyond where you collected. Okay? So that would be like saying, we collected all this data on finger size, and then we say, well, since finger sizes in here are that way, I'm sure it's exactly the same with kids. Well, we don't know that. We didn't check that data. It might be, but that would be extrapolating. Interpolating, when we get our line a little bit, we'll be able to do some predicting and say, based on your finger size, how big shoes you have or how tall you are. Okay? So there's interpolation, good. Extrapolation, bad. Outlier is an extremely deviant individual. We know what outliers are. We've seen those. And they seriously affect the correlation coefficient, because like somebody with size 18 feet, it's going to affect it. So people, when they're doing studies, decide, do I keep this in here or is this extreme enough? And there's actually guidelines for